Have you ever wondered why your coffee sits perfectly still in its cup, even though you're spinning at over 1,000 miles per hour? Right now, as you listen to these words, you are racing through space on a planet that turns relentlessly beneath your feet. The Earth spins at 1,037 miles per hour at the equator. It hurtles around the sun at 67,000 miles per hour. Yet somehow, the air around you doesn't rush past your face. The water in your glass doesn't slosh. Your heartbeat remains steady. It's as if you exist in a pocket of absolute stillness, within a universe drunk on motion. The entire solar system sails through the galaxy at nearly 500,000 miles per hour. But what if that stillness is the deepest illusion of all? What if everything that feels solid and permanent is actually caught in an ancient dance that began before atoms existed? What if the very reason you can take a breath right now depends on forces spinning so fast they bend the fabric of time itself? Tonight, we journey into the spinning heart of everything. We'll discover why motion might be the most fundamental property of existence, why the universe seems incapable of standing still, and perhaps, most surprisingly, why that endless turning might be the only reason you're here to wonder about it at all. Now let's drift into our first mystery. Why do we feel motionless in a universe that never stops moving? Picture this moment as if you could step outside of it. You're sitting or standing on the surface of a massive sphere. That sphere rotates once every 24 hours. As it turns, you move with it at speeds that would make highway travel seem leisurely. Yet your coffee doesn't know it's flying through space. Your pen doesn't slide across the table. The air doesn't howl past your ears like a cosmic hurricane. This is one of nature's most elegant deceptions, an illusion so complete that it fooled humanity for thousands of years. The secret lies in a principle so simple, it hides in plain sight. Everything moves together. Your body, the chair beneath you, the air you breathe, the building around you, even the atmosphere that wraps our planet like a gossamer shell. All of it spins as one. There's no relative motion between you and your immediate surroundings, no difference in velocity to create the sensation of movement. Isaac Newton first described this phenomenon in the 17th century. An object in motion stays in motion unless something pushes against it. Since everything on Earth shares the same rotational velocity, nothing pushes against anything else. The motion becomes invisible. It's the same reason you can sip tea while sitting in an airplane cruising at 500 miles per hour. You and the aircraft move as a single unit through the sky. Only when turbulence disrupts that unity do you suddenly feel the speed. Earth's rotation is even more seamless than flight. No air resistance exists in the vacuum of space. No friction slows the planet's ancient spin. For over 4 billion years, this world has turned with mechanical precision. The same smooth revolution that existed when the first microbes appeared in primordial oceans. Our senses evolved to navigate a much smaller world. They detect walking, running, falling. The acceleration of starting to move, the deceleration of coming to rest. But they cannot perceive constant velocity. Your inner ear, that delicate organ of balance, responds only to changes in motion. It evolved to help our ancestors climb trees and navigate terrain, not to sense the rotation of an entire planet, so we remain blissfully unaware of our cosmic journey. Yet scientists have found ways to make the invisible visible. The Foucault pendulum, first demonstrated in 1851, swings freely while the Earth turns beneath it. Over hours, its path appears to rotate. In truth, the pendulum maintains its direction while the ground shifts below. It's Earth's rotation made manifest in the gentle arc of a swinging weight. Standing near one of these devices in a museum, becomes an almost spiritual experience. You witness time and motion converging, the planet's spin visualized in real time. Each swing a reminder that stillness is relative, motion is fundamental. This rotation isn't merely Earth's quirk. It's a cosmic signature written into the structure of reality. When massive stars collapse, they spin faster as they shrink. Angular momentum must be conserved. Like a figure skater pulling her arms close to her body, every planet inherits rotational energy from the swirling disk of dust and gas that formed it. Our 24-hour day is a fossilized memory of that ancient whirlpool. The sun itself rotates once every 27 days. Its magnetic field spirals through space like luminous silk. The Milky Way, our galactic home, completes one revolution every 230 million years. Hundreds of billions of stars dancing in a spiral pattern older than our solar system. Even distant galaxies captured by the James Webb Space Telescope show signs of rotation. Light from these cosmic islands has traveled for over 13 billion years, yet astronomers can detect subtle color shifts that reveal their spin. One side approaching us slightly, tinted blue, the other receding, shifted toward red. The tendency to rotate seems encoded in the universe's deepest laws. But why don't we feel any of this motion? Part of the answer lies in Einstein's insight about relativity. There is no absolute motion, only motion relative to something else. From our perspective, we are at rest. The universe revolves around us. From another reference frame, we are the ones in motion. Both views are equally valid. This symmetry keeps the laws of physics consistent everywhere. It also preserves our sanity. If we could somehow feel Earth's rotation, the sun's gravitational pull, the galaxies drift through space, our perception of time itself would shatter. Because motion and time are intimately connected. The planet's spin defines our days. Its orbit creates our years. These rhythms shape not just our calendars, but our biology. Every cell in your body operates on circadian cycles synchronized to Earth's rotation. The stillness you experience right now is not the absence of motion. It's the harmony of everything moving together. You are not standing on solid ground. You're gliding through a cosmic river. Every breath you take happens while racing through space at incomprehensible speeds. The silence around you is the sound of perfect synchronization. A universe moving so smoothly that motion feels like rest. Take a moment to absorb this. Close your eyes. Feel the apparent stillness. Now remember that you're spinning. Always have been. The quiet you hear is actually the whisper of everything turning in unison. And in that perfect balance between motion and calm, something remarkable becomes possible. Life itself. But this raises a deeper question. If everything in the universe spins, what set it all in motion? Who gave the cosmos its first turn? Let's travel backward to the very beginning to find out. What gave the universe its first spin? Imagine you could rewind time, not just centuries or millennia, but all the way back to the first fraction of a second after existence began. What would you witness? Would there be light, sound, or would there only be a sudden swirl, a primordial twist, the very first rotation in the history of everything? The question of cosmic spin takes us to the frontier of physics, to moments so early that our current understanding barely applies. Scientists call this the Planck era, a window lasting only 10 to the power of minus 43 seconds after the Big Bang, a time span so brief that even light cannot cross the distance of a proton. Yet within that infinitesimal moment, the seeds of all future motion may have been planted. Today's most sophisticated instruments detect faint traces of that ancient beginning. The cosmic microwave background, the afterglow of creation itself, carries subtle patterns, tiny temperature variations only millionths of a degree apart. These ripples in the fabric of space-time grew into everything we see: galaxies, stars, planets, life. But some researchers have noticed something intriguing in those patterns: a faint alignment, a large-scale twist in how the ripples are distributed across the sky. They call it the axis of evil, not because it's malevolent, but because it challenges our assumptions about cosmic uniformity. This mysterious alignment could be evidence that the entire universe once possessed a subtle rotation. If true, that primordial spin would have influenced the formation of every structure in existence, from the spiral arms of galaxies to the arrow of time itself. How could such rotation begin? The answer may lie in quantum fluctuations. Even in perfect emptiness, energy fluctuates randomly at the smallest scales. When the Big Bang occurred, cosmic inflation stretched those fluctuations across vast distances. That rapid expansion could have turned some random jitters into organized rotational motions. The first cosmic spins. Inflation theory, proposed by Alan Guth in the 1980s, explains why the universe appears so smooth, yet still contains seeds of structure. Recent observations by the Planck satellite and BICEP, two experiments, suggest that during inflation, subtle rotational modes may have existed in primordial gravitational waves. These are called B modes, tiny curls in space-time that could be fossil records of the universe's first rotation. They hint that the Big Bang was not just an explosion, it was a twisting birth, one that imprinted spin across every scale of matter. This makes profound sense when we consider what happened next. As the universe expanded and cooled, particles began forming, first quarks and gluons, then protons and neutrons, finally atoms. Each carried microscopic amounts of angular momentum inherited from those earliest moments. When gravity later gathered them into clouds and stars, that ancient rotation was preserved. It's the same principle that makes a figure skater spin faster when she pulls her arms inward. In physics, angular momentum cannot simply vanish. Motion must come from motion. So the first spin, however tiny, had to exist from the very beginning. Astronomers today can see fingerprints of that primordial rotation in distant galaxies. Studies of thousands of spiral galaxies reveal subtle preferences in their rotational directions, a cosmic handedness that might trace back to the universe's earliest moments. While not yet conclusive, this asymmetry suggests our cosmos is not entirely random. There may be a hidden rhythm, a silent turn that everything still follows. Even dark matter, the invisible scaffolding holding galaxies together, appears to carry rotational signatures. Computer simulations show dark matter halos, twisting over billions of years, guiding visible galaxies like whirlpools directing leaves on their surfaces. Without that rotation, galaxies would fly apart. The early universe seems to have set everything spinning. Even now, echoes of that motion keep stars in their orbits. The origin of cosmic spin points to a deeper principle: symmetry breaking. In the earliest moments, forces we now know as gravity, electromagnetism, and nuclear interactions were unified. As the universe cooled, they separated. When perfect symmetry broke, tiny imperfections appeared. Those imperfections, according to cosmological theory, allowed structure and motion to exist. In a perfectly balanced universe, nothing could move. But in a slightly unbalanced one, everything could dance. We see this principle reflected throughout nature. in the direction galaxies spiral, in how atoms organize their electron shells, even in the left-handed preference of neutrinos. Nature, it seems, is not perfectly symmetrical. That tiny bias is what allows everything to turn. Some scientists have attempted to detect whether the entire universe is rotating. Analysis of hundreds of thousands of galaxies from sky surveys reveals intriguing patterns. Galaxies in one hemisphere of the sky show different rotational preferences than those in the other. This could suggest large-scale cosmic spin, not like a spinning top, but as a subtle twist in the fabric of space-time itself. Even a minute rotation could cascade across billions of light-years. To us, it would feel invisible, but on universal scales, it might shape the geometry of everything. The James Webb Space Telescope now captures light from galaxies that formed just 300 million years after the Big Bang. Some already show organized rotation, spiral patterns appearing far too early to be explained by random processes. This means the seeds of spin were planted almost immediately. The universe didn't learn to rotate, it was born turning. Even on quantum scales, spin is fundamental. Every particle carries intrinsic angular momentum. Electrons, protons, neutrons all possess quantum spin. Not physical rotation as we imagine it, but a mathematical property encoded in their wave functions. As physicist Richard Feynman observed, particles don't spin like tiny tops. They simply have spin, as they have mass. It's a built-in feature of matter itself. So rotation wasn't added to the universe later. It was part of the original blueprint. When you look at the night sky, you're seeing the inheritance of that first cosmic motion. Every galaxy's spiral arms, every planet's orbit, every photon of light streaming toward your eyes, all descended from that primordial rotation. Without it, matter would never have clumped together. Stars would never have formed. Time itself would have no rhythm. Motion is not an accident of existence. It's the heartbeat of reality. Though we may never know exactly what triggered the first spin, evidence whispers that it was always there. Quiet, steady, invisible, yet written into everything we observe. The universe carries memory, not in words, but in patterns of motion. Within those patterns lies the signature of the first turn, a twist older than time itself. So when we ask what gave the universe its first spin, perhaps the most honest answer is this: the universe never learned to move. It was born already in motion. Spin wasn't created, it was inherited. Take a breath. The atoms in your body are still turning with that original impulse. From the tiniest electron to the spiral of the Milky Way, the same rotation continues, unbroken for nearly 14 billion years. We are not separate from that motion, we are its continuation. And as we move deeper into this story, we encounter an even more profound question. If rotation shaped the birth of the universe, could it also be the reason life itself exists? That's where our journey leads next. Did spinning make life possible? Without rotation, Earth would be a world of extremes. One side scorched by eternal daylight, the other frozen in perpetual darkness. Between them, a violent boundary of storms. No stable climates, no gentle seasons, no life as we know it. But because our planet spins, it breathes. Every sunrise, every breeze, every raindrop exists because of that ancient rotation that began 4.5 billion years ago. Earth's spin is more than motion. It's an engine of life itself, a delicate balance that sustains everything we consider normal, from the magnetic field that shields us from cosmic radiation to the temperature cycles that nurture oceans and clouds. Rotation shapes our world in ways both obvious and invisible. Near the equator, our planet's surface moves at 1,037 miles per hour, completing one full rotation every 23 hours, 56 minutes, and 4 seconds. This is called a sidereal day, the true measure of Earth's spin relative to distant stars. This steady rhythm sets the tempo for all biological and environmental cycles. Every plant, animal, and weather system synchronizes to this cosmic metronome. The first gift of Earth's rotation is the alternation of day and night. Sunlight distributes evenly across the surface over time, creating temperature gradients that drive wind, ocean currents, and weather patterns. Without daily rotation, one hemisphere would bake under endless solar bombardment, temperatures soaring beyond what any known life could withstand. The other side would plunge into permanent freeze, colder than the most barren Arctic wasteland. The boundary between these extremes would be a twilight zone of perpetual storms, a belt of chaos where superheated air meets frozen atmosphere. Nothing could survive such violence. But Earth's spin changes everything. The sun rises and sets. Energy spreads gently across continents and oceans. Stable climates emerge. Habitable regions flourish. Life finds its footing in the rhythm of rotation. Spin also powers our planet's magnetic field. Deep beneath your feet, Earth's liquid iron core churns and flows. This motion generates electric currents. Those currents create magnetic fields. The result is a protective bubble that surrounds our entire world. This magnetosphere deflects the solar wind, a constant stream of charged particles blasted toward us by the sun. Without this shield, those particles would strip away our atmosphere, molecule by molecule, breath by breath, until nothing remained but barren rock. We know this can happen because we've watched it elsewhere. Mars once had a thicker atmosphere, perhaps even liquid water on its surface. But as its smaller core cooled, the internal motion that powered its magnetic field slowed, eventually stopped. The protective barrier failed. Solar radiation scoured away the Martian air, leaving behind the cold, dry desert we see today. Here on Earth, our magnetic field still thrives. It creates the auroras, those shimmering curtains of light near the poles. They're not just beautiful, they're proof of protection, visual evidence that our planet's rotation still powers an invisible force field around us. But the influence of spin extends far beyond magnetic shielding. Earth's rotation shapes the very air we breathe, because our planet turns. Moving air curves as it travels. This is called the Coriolis effect. It creates the vast, spiraling systems that define weather, hurricanes spinning in the Atlantic, jet streams flowing around the globe, ocean currents carrying warm water toward the poles and cold water toward the tropics. Without the Coriolis effect, weather patterns would collapse into chaos. Storms couldn't organize. Heat couldn't redistribute efficiently. Climates would become wildly unstable. The speed of rotation directly determines how stable a planet's climate can be. Computer simulations of worlds with different spin rates reveal dramatic differences. Too slow, and one side overheats while the other freezes. Too fast and extreme winds dominate everything. Storms rage constantly. Day lengths become so short that atmospheric systems can't establish equilibrium. Earth's 24-hour rhythm hits a perfect balance, long enough to distribute solar energy evenly, short enough to prevent dangerous temperature extremes. This rotational rhythm also influences life directly. Living organisms evolved internal clocks, synchronized to Earth's spin, circadian rhythms that govern when plants open their leaves, when animals sleep and wake, when cellular repair processes activate, when hormones release into bloodstreams. Research shows that every cell carries molecular timekeepers, proteins that oscillate with roughly 24-hour periods. These biological clocks existed in the earliest life forms. They've been refined over billions of years of evolution. If Earth stopped rotating, this ancient harmony would shatter. The steady alternation of light and dark would end. Organisms would struggle to adapt. Ecosystems would collapse. Life as we know it could not continue. Rotation also shaped our relationship with the Moon. Billions of years ago, a Mars-sized object called Theia collided with the young Earth. The impact sent debris into orbit. That debris eventually coalesced into our lunar companion. The collision also dramatically increased Earth's spin. In those early days, a single day lasted only about 6 hours. Over eons, the Moon's gravity has been slowing that rotation, gradually stretching our days to their current 24-hour length. Tidal forces between Earth and Moon keep our planet's axial tilt stable. This prevents extreme climate variations that would occur if our world wobbled chaotically. The Moon and Earth exist in a slow gravitational dance. The same tides that rise and fall in our oceans also slow our planet's spin, adding about 1.7 milliseconds to each day every century. It's a reminder that even our most fundamental rhythms are slowly changing, one imperceptible moment at a time. Looking beyond Earth, we see how rotation affects habitability throughout the solar system. Jupiter spins once every 9 hours and 56 minutes, the fastest rotation of any planet. This rapid spin drives ferocious atmospheric dynamics, jet streams racing at hundreds of miles per hour. The Great Red Spot, a storm larger than Earth that has raged for centuries. Rotation there creates chaos, yet also distributes heat, preventing any one region from becoming too extreme. Venus represents the opposite extreme. It rotates backward and extremely slowly. One Venus day lasts 243 Earth days. This sluggish spin contributes to its runaway greenhouse effect. Heat cannot distribute efficiently. The planet's thick carbon dioxide atmosphere traps solar energy. Surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. The comparison is striking. Too fast and atmospheric violence dominates. Too slow, and heat becomes trapped, creating hellish conditions. Mars offers another cautionary tale. Its day is only 40 minutes longer than Earth's. But as its core cooled billions of years ago, the internal motion that powered its magnetic dynamo faded. Without magnetic protection, solar radiation gradually stripped away its atmosphere. Today, only faint magnetic signatures remain in the Martian crust, ghostly traces of the rotation that once sustained a more dynamic world. These examples demonstrate that rotation is not optional for habitability. It's fundamental. Recent observations of exoplanets confirm this pattern. Worlds with detectable atmospheric circulation show better temperature distribution, more stable climates, greater potential for liquid water. Planets that rotate rapidly enough to maintain molten cores keep their magnetic fields longer. Those fields protect atmospheres from stellar radiation, creating conditions where life might take hold. So when we ask whether spinning made life possible, the evidence is overwhelming. Rotation shapes everything from day length to magnetic protection, from weather patterns to biological rhythms. Life doesn't just tolerate motion, it depends on it. Our world's spin has changed over geological time, but its effects continue echoing through every aspect of existence. It controls ocean tides, it guides the growth of forests, it triggers animal migrations, it defines our very sense of time, not as an abstract concept, but as the physical turning of our world. As one scientist observed, We are not just in the universe, we are of the universe. Earth turns, and so do we. Take a moment to feel that rotation. Listen to its whisper. Every spin carries 4.5 billion years of balance and motion. If Earth stopped turning tomorrow, oceans would surge toward the poles. The atmosphere would collapse into chaos. Our planet would lose its breath. But tonight, as it spins gently beneath you, everything works perfectly, quietly, continuously. The rotation of Earth is the invisible architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into weather, into seasons, into the rhythm of your heartbeat. But there's something even more remarkable about rotation. Beyond a certain speed, spinning objects don't just move through space. They begin to warp the fabric of space and time itself. And that's where our story takes an extraordinary turn. Can rotation bend time itself? At extreme speeds, rotation transcends motion and becomes something far stranger. It begins to distort the very geometry of space-time. Einstein's general theory of relativity revealed that gravity and acceleration are fundamentally the same phenomenon. Both arise from the curvature of space-time itself. When massive objects spin rapidly, they drag space-time along with them, like honey swirling around a spoon. This effect is called frame dragging, and it's one of the most profound and verified predictions of modern physics. Imagine space-time as a calm lake. When a massive object rotates, it stirs that lake, creating tiny vortices in the flow of time itself. Within those whirlpools, the very direction of time begins to curve. NASA's gravity probe, B experiment, launched in 2004, measured this effect around Earth. 4 ultra-precise gyroscopes orbited 400 miles above our planet for over a year. The data confirmed that Earth's rotation drags space-time by about 39 milliseconds per year, a minuscule amount, but it matches Einstein's equations perfectly. Even our gently spinning planet is capable of bending the flow of time. Now imagine rotation billions of times faster, gravitational fields billions of times stronger. This is what happens near neutron stars. When a massive star dies, it collapses under its own gravity. Protons and electrons merge into neutrons. The result is an object only 12 miles wide, but containing more mass than our Sun. To conserve angular momentum, these stellar remnants spin incredibly fast. Some rotate 700 times per second. They're called pulsars because their magnetic poles emit beams of radiation. As they spin, those beams sweep across space like cosmic lighthouses. The magnetic fields around pulsars are trillions of times stronger than Earth's. They twist space-time so violently that even light struggles to travel in straight lines. Time itself runs slower near these objects. The stronger the spin, the slower the clock. This isn't science fiction. It's gravitational time dilation, a direct consequence of Einstein's insights about space, time, and motion. When you're close to a rapidly spinning massive object, you cannot remain stationary. Space-time itself drags you along, forces you to rotate with it. This effect becomes even more extreme near spinning black holes. Kerr black holes, named after mathematician Roy Kerr, represent the ultimate expression of rotation in the universe. Unlike simple black holes that merely pull everything inward, Kerr black holes spin space-time around their axis. Close to the event horizon, that rotation approaches the speed of light. Nothing, not even time itself, can resist being dragged along. The region outside the event horizon where this frame dragging occurs is called the ergosphere. Within it, nothing can remain motionless relative to distant space. Every particle, every photon must rotate with the black hole. It's as if space itself becomes liquid, spinning in a vast, invisible whirlpool. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. The glowing ring we see isn't light from the black hole itself. It's radiation from matter spiraling around it, light bent and delayed by space-time curvature. Those luminous arcs are visual proof that rotation and gravity together can bend not just matter, but the flow of time. Even here on Earth, we experience these effects daily. GPS satellites orbiting our planet must constantly correct for time dilation, both gravitational and velocity-induced. If left unadjusted, GPS clocks would drift by 38 microseconds per day, enough to cause navigation errors of several miles. So the bending of time isn't just theoretical, it's part of everyday technology. When astrophysicists model the extreme environments near spinning black holes, the mathematics becomes breathtaking. Rotation can twist space-time so sharply that closed time-like curves appear, paths where particles could theoretically loop back to earlier points in time. Whether such loops are physically possible remains uncertain, but they emerge naturally from Einstein's equations. In these extreme environments, past and future lose their fixed meaning. The James Webb Space Telescope now observes the accretion disks of distant quasars, galaxies powered by supermassive rotating black holes. The spectra show light stretched and redshifted, evidence that time runs slower in those regions. Some of this light left its source over 13 billion years ago. We're watching time itself stretched across the cosmos. Rotation doesn't just shape matter, it defines how time flows near spinning objects. The faster and more massive the spin, the greater the warping of space-time. From our gentle planet to the violent hearts of galaxies, the universe uses rotation to sculpt both motion and duration. What we call now is different everywhere, depending on how fast and how deep the local space-time is turning. Even light, which normally travels at the universe's ultimate speed limit, bends and slows near rotating masses. X-ray observatories have captured echoes around black holes, light temporarily trapped in rotation before escaping. In these echoes, time stretches like a soft thread, measurable, predictable, yet endlessly strange. One might wonder whether the universe itself twists time on a grand scale. Large-scale cosmic rotation could subtly influence how time flows across billions of light years. Current data shows no strong evidence for universal spin, but the question remains open. Even the faintest twist over cosmic distances might leave fingerprints in ancient light, hints that time itself has a preferred direction. As physicist Kip Thorne explained in The Warped Space-Time Near a Spinning Black Hole, the future of one observer can become the past of another. Rotation doesn't just bend trajectories, it bends the sequence of events, the very rhythm of existence. Yet for all its strangeness, this effect follows consistent, measurable laws. Time dilation around rotating bodies has been verified by atomic clocks on aircraft, satellites in orbit, experiments in mountain laboratories. The faster you move or the deeper you sink into gravity's well, the slower your time flows. It's not illusion. It's the universe maintaining perfect balance. So yes, rotation can bend time. But what's even more intriguing is how that bending reveals a deeper pattern, a universal law linking motion, gravity, and energy into one seamless whole. From Einstein's equations to every ticking satellite, it all points to one profound truth. The universe doesn't just move through time, it creates time through motion. Take a slow breath. Right now, your sense of time is tied to Earth's gentle spin, the sun's gravitational pull, the galaxy's ancient rotation. You exist within motion so precise it writes the seconds of your life. If rotation can bend time, what happens when we discover that time itself might control the spin? That mystery awaits us in our final chapter. If spin controls time, who controls the spin? Every second you experience is shaped by motion, the ticking of clocks, the rhythm of your heartbeat, the pulse of cellular processes, all depend on something, somewhere, spinning. Electrons orbit atomic nuclei at precise energy levels. Earth rotates once every 24 hours. As it spins, it drags space-time just enough to alter how time flows. At the equator, where our planet's surface moves fastest, clocks run slightly slower than those at the poles. Not because of temperature or atmospheric pressure, because of relativity. Einstein showed that motion and gravity and stretch or compress time depending on velocity and gravitational depth. So yes, spin controls time. But the deeper question remains: what controls the spin? To answer this, we must examine the most precise timekeepers humanity has ever built: atomic clocks. Inside these devices, electrons whirl around atomic nuclei at fixed energy levels. When they transition between those levels, they emit photons at exact frequencies. That frequency, measured in cesium-133 atoms, defines our standard second: 9,192,631,770 cycles of radiation, corresponding to a specific quantum transition. These words, established by international agreement, describe how every second of your life is calibrated to atomic spin. But this isn't the classical rotation of planets or wheels. It's quantum spin, a fundamental property of matter itself. In quantum mechanics, particles carry intrinsic angular momentum, not because they physically rotate like tiny tops, but because spin is built into their mathematical description, their wave functions. This quantum spin determines how particles behave in magnetic fields, how they bond with other particles, even how they obey the Pauli exclusion principle, the rule that no two electrons can occupy identical quantum states. So at its deepest level, timekeeping depends on the internal angular momentum of atoms themselves. But quantum spins govern time in laboratories. Planetary spins govern time on cosmic scales. Earth's rotation defines the length of our days. Its orbit around the sun creates our years. These motions aren't fixed. They slowly drift over centuries and millennia. Tidal forces from the moon gradually slow Earth's spin, adding 1.7 milliseconds to each day every century. To keep atomic time and planetary time synchronized, scientists use leap seconds, occasionally adjusting the world's clocks by 1 second, ensuring that noon still corresponds to the sun's highest point in the sky. This reveals something profound about the nature of time. It's not absolute, not uniform everywhere. Instead, it emerges from the interplay of different rotational systems: quantum, planetary, stellar, galactic, each contributing to the complex symphony we call temporal flow. The Earth's slowing rotation means our days are gradually lengthening. In the distant past, when the moon was closer, days lasted only about 6 hours. Tidal forces have been stretching them ever since. In the far future, if both worlds survive, Earth and Moon will become tidally locked, each showing only one face to the other. Days and months will both last about 47 current Earth days. The dance between celestial bodies shapes the very rhythm of time, but even on larger scales, rotation influences temporal flow. Our solar system orbits the galactic center once every 230 million years. This galactic year provides yet another timepiece. a cosmic calendar marking epochs in Earth's history. The last time we were in this position relative to the galaxy's center, dinosaurs were just beginning to dominate the planet. The Milky Way itself may be part of an even larger rotational system, groups and clusters of galaxies moving in vast cosmic streams. Each level of organization adds its own contribution to the universe's temporal structure. Modern physics reveals that time and motion are inseparable. Special relativity shows that time slows for objects moving at high speeds. General relativity demonstrates that massive objects warp space-time, creating regions where time flows at different rates. Rotation combines both effects. Spinning objects move rapidly at their surfaces. They also concentrate mass and energy. Both factors contribute to temporal distortion. The faster something spins, the more it affects the flow of time nearby. This principle operates from quantum scales to cosmic ones. Inside atomic nuclei, rapid particle motions contribute to nuclear binding energies. Around black holes, extreme rotation creates the most severe time dilation known. In both cases, motion defines how time unfolds. But here's where the mystery deepens. If motion controls time and time provides the framework for measuring motion, we encounter a profound circular relationship. Time is defined by counting regular motions, atomic transitions, pendulum swings, planetary rotations. Yet those motions occur within time. They require temporal duration to be meaningful. Which comes first, motion or time? The answer appears to be that neither has primacy. They're co-emergent properties of a deeper reality, space-time itself. Einstein's insight was that space and time form a unified fabric. Matter and energy curve this fabric. Curvature guides the motion of matter and energy. It's a self-consistent loop where geometry, motion, and temporal flow arise together. In this view, asking who controls spin is like asking who controls the curvature of space-time. The universe as a whole determines its own geometry. Through the collective gravitational effects of all matter and energy, there's no external agent pulling strings, no cosmic puppeteer setting everything in motion. Instead, the universe is self-organizing, each part influencing every other part through gravitational and electromagnetic forces. This self-organization extends to the quantum realm. Particle spins aren't assigned by some external mechanism. They emerge from the symmetries of space-time itself. Quantum field theory shows that spin is a consequence of rotational symmetry, the fact that physical laws remain unchanged when we rotate our coordinate system. This deep connection between symmetry and spin suggests that rotation is built into the fundamental structure of reality. It's not something added to the universe. It's something the universe cannot avoid having. Even attempts to create perfectly static, non-rotating systems fail. Quantum fluctuations ensure that some angular momentum always exists. The uncertainty principle guarantees that particles cannot be completely at rest. There's always residual motion, residual spin, residual temporal flow. So when we ask who controls the spin, perhaps the most honest answer is this: the universe controls its own spin. Through the collective interaction of all its parts, each galaxy, star, planet, atom, and particle contributes to the total. The result is a cosmos in perpetual motion, where time emerges from the interplay of countless rotations. From quantum fluctuations to galactic dynamics, all participating in a vast, self-regulating temporal symphony. Your heartbeat synchronizes to Earth's rotation. Earth's rotation couples to lunar tides. Lunar tides connect to solar gravitational effects. Solar motion follows galactic orbital mechanics. Galactic dynamics respond to dark matter distributions. Dark matter clustering reflects primordial density fluctuations. Those fluctuations trace back to quantum processes during cosmic inflation, its motion all the way down and all the way up. In this interconnected web, you are not separate from cosmic rotation. You are part of it. The atoms in your body formed in stellar cores. Those cores spun as they fused heavier elements. The angular momentum of ancient stars flows through your cellular processes. Your biological rhythms echo planetary cycles. Your lifetime unfolds within galactic time. You exist at the intersection of multiple spinning systems, each contributing to your moment-to-moment experience of temporal flow. The question isn't who controls the spin. It's how all these spins coordinate to create the remarkably stable temporal environment where consciousness can emerge and contemplate its own existence. The universe has organized itself so precisely that beings like you can arise within it. Beings capable of measuring time, of questioning motion, of discovering the deep relationships between spin, gravity, and temporal flow. In a sense, through you, the cosmos has become aware of its own rotation. Take a moment to absorb this. You are the universe's way of understanding its own motion. Every breath you take participates in cosmic rhythm. Every thought you think emerges from the interplay of countless spinning systems. You are not a passive observer of rotation. You are rotation observing itself. And in that recognition lies perhaps the deepest comfort of all. You belong here. You are part of the eternal dance. Your existence is both consequence and continuation of the same cosmic motion that began before atoms, before light, before memory. The spinning never stops. The dance never ends. And within that endless turning, you have found your place, your rhythm, your home in the vast symphony of everything that moves. Rest in that knowledge. You are exactly where and when you belong, spinning gently through space and time, part of something infinitely larger than yourself, yet intimately connected to every rotation in the universe. The cosmos turns. You turn with it, and in that shared motion, all is well. But this perfect synchronization hides something stranger still, something that touches the very nature of what we call time itself. Because time, as it turns out, is not what you think it is. It's not absolute, not uniform, not independent of motion. Time is recorded in the spin of everything that moves, and the faster something spins, the more it bends the fabric of reality around it. Right now, there are clocks scattered across Earth that disagree with each other, not because they're broken, but because time itself flows at different rates depending on where you are and how fast you're moving. A clock sitting at sea level near the equator runs slightly slower than one placed high in the mountains. The difference is microscopic, a few nanoseconds per day, but it's real, measurable, undeniable. At the equator, you're moving faster through space because Earth's rotation is greatest there, over 1,000 miles per hour. This velocity, combined with Earth's gravitational pull, creates a subtle distortion in space-time. Time itself slows down, not by much, but enough that atomic clocks can detect it. Einstein predicted this over a century ago with his theories of relativity. Special relativity showed that time slows for objects in motion. General relativity revealed that gravity warps the flow of time. At Earth's surface, both effects work together. The faster you move, the slower your clock ticks. The deeper you are in a gravitational well, the slower time passes. This isn't just theory. It's the reason your phone knows where you are. Every time you check a map, you're witnessing Einstein's equations at work. The global positioning system relies on a constellation of satellites orbiting Earth, 24 spacecraft circling the planet at about 12,500 miles above the surface. Up there, they move at nearly 9,000 miles per hour. They experience weaker gravity than we do down here. Both factors affect how time flows for them. Without corrections, their onboard atomic clocks would drift faster than ours by about 38 microseconds each day. That might sound trivial, but in GPS terms, it would create navigation errors of several miles within hours. Engineers compensate for this by programming the satellite's clocks to tick at a slightly different rate. They literally adjust time itself to keep the system accurate. Every position signal you receive has been corrected for the curvature of space-time caused by Earth's rotation and gravity. So when you follow directions to a coffee shop, you're relying on humanity's understanding of how motion bends time. A quiet collaboration between physics and everyday life. But who started all this spinning in the first place? Who gave Earth its rotation? Who set the satellites in motion? Who spun the first atom? The answer leads us back to a principle so fundamental it governs everything from galaxies to electrons. Angular momentum. In physics, angular momentum is the measure of rotational motion. It's a conserved quantity, meaning once it exists, it cannot be destroyed, only transferred from one object to another. 4.6 billion years ago, our solar system didn't exist. In its place was a vast cloud of gas and dust, cold, dark, slowly rotating. Gravity pulled the cloud inward. As it collapsed, it began to spin faster. This is the same principle that makes a figure skater spin faster when they pull their arms close to their body. As the cloud shrank, its rotation accelerated. The angular momentum had to go somewhere. It couldn't simply disappear, so it distributed itself throughout the forming solar system. The sun inherited most of it. The planets received their share. Moons, asteroids, even comets all carry fragments of that primordial spin. Earth's 24-hour rotation is a fossilized memory of that ancient whirlpool, an echo of motion that began before rocks existed, before water flowed, before life took its first breath. And here's the remarkable thing. No external force is needed to keep it going. Once set in motion, objects continue spinning because of inertia, the same law that keeps a planet moving through space until something resists it. In the vacuum of space, friction is nearly absent. Nothing slows the ancient rotations, so they persist. For billions of years, the Earth has been turning since before continents formed. It will continue turning long after we're gone. The sun rotates once every 27 days at its equator, but not uniformly. Its poles spin slower. This differential rotation creates something extraordinary. Twisted magnetic fields that spiral through space like invisible silk. These fields generate solar flares, coronal mass ejections, bursts of charged particles that race toward Earth. When they arrive, they distort our planet's magnetic field, create auroras in the polar skies, sometimes disrupt satellites and power grids, all because the sun cannot spin evenly. Its rotation sculpts the electromagnetic landscape of our entire solar system. From atomic scales to stellar scales, spin is never passive. It shapes magnetic fields, defines rhythms, interacts with the very fabric of space-time. Einstein's equations showed that the geometry of space-time depends on energy and momentum, including angular momentum. Spin curves time, remove all rotation, and space-time becomes simpler, flatter, less dynamic. Add spin and it warps, gently for planets, violently for black holes. In 2011, NASA launched Gravity Probe B, a satellite designed to measure how Earth's rotation affects the space around it. The results confirmed Einstein's prediction. Earth's spin drags space-time along with it, like a spoon stirring honey. The effect is tiny, but it's there. Your body exists within this subtle twist. Every movement you make occurs in a space-time already curved by the planet's ancient rotation. This phenomenon is called frame dragging. It means that massive rotating objects don't just sit in space, they twist the very structure of reality around them. The faster the spin, the greater the distortion. Near a spinning black hole, this effect becomes extreme. The black hole's rotation creates a region called the ergosphere, a zone where space-time itself is dragged so violently that nothing can remain stationary. Even light gets swept along. Time and space blend in ways that defy intuition. Clocks slow. Directions become meaningless. The boundary between now and later blurs into something unrecognizable. Yet the principle is the same one that governs a child's spinning top. Angular momentum warps the world around it. But if spin governs time and spin itself arises naturally from the conservation of motion, then who controls it? The most honest answer science can offer is this: the universe controls itself. Every spin is balanced by another. Every slowing rotation is matched by a transfer of momentum elsewhere. Even the smallest quantum particle obeys these equations, ensuring that angular momentum remains perfectly conserved across space and time. NASA's Jet Propulsion Laboratory puts it simply: the laws of motion don't change. The universe runs on balance. What is lost in one place is gained in another. There's no master clock, no hidden hand setting the cosmic metronome. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope, its built-in mechanism for keeping everything aligned. From quarks to galaxies, the same principle governs every scale. Even when systems decay, collide, or slow down, their angular momentum transfers onward, keeping the cosmic rhythm alive. In 2016, the European Space Agency's Gaia mission mapped the precise motions of over 1 billion stars in the Milky Way. The data revealed patterns of rotation stretching across hundreds of thousands of light-years. Our entire galaxy completes one revolution every 230 million years, carrying the Sun and its planets along in a vast spiral. Each star's orbit contributes to this grand cosmic timepiece, one rotation marking what astronomers call a galactic year. The last time we were in this position relative to the galaxy's center, dinosaurs were just beginning their reign on Earth. Think about that for a moment. The solar system has circled the Milky Way's heart only a handful of times since complex life began. We exist on a planet that orbits a star, that orbits a galaxy, wheels within wheels, rotations nested inside rotations, and all of it connected by the same principle that keeps electrons spinning around atomic nuclei. Just as atomic spin defines the second, stellar spin defines eons. The universe measures itself through motion. In 2022, the James Webb Space Telescope peered deeper into space than ever before. It observed galaxies whose light has traveled for over 13 billion years. Galaxies that formed when the universe was still young, still finding its shape. And even in those primordial structures, astronomers detected rotation, evidence that angular momentum existed almost immediately after the Big Bang. This suggests something profound. The law connecting spin and time has been operational since the universe's earliest moments. Spin is not a product of time, it's part of what gives time its flow. Without rotation, the universe would have no internal clock, no way to mark progression, no rhythm to carry existence forward. So when we ask who or what controls the spin, we're asking the wrong question, because spin doesn't need a controller. It emerges naturally from the fundamental symmetries of space-time, from the conservation laws written into the fabric of reality itself. Every rotation you observe, whether in a distant galaxy or in the electrons flowing through your neurons, is part of a self-sustaining system, a universe that maintains its own balance, without intervention, without guidance, simply by being what it is. Take a breath. Feel the stillness in your chest as your lungs expand. Now remember, the atoms within you are spinning. The planet beneath you is spinning. The star that warms you is spinning. The galaxy that holds you is spinning, all of it synchronized in a harmony so perfect you can't perceive the motion. You are not separate from this dance. You are woven into it. Every heartbeat participates in the cosmic rhythm that began before light, before atoms, before time itself had a name. And this raises perhaps the most beautiful mystery of all. If the universe is a self-regulating system of endless rotations, what happens when that perfect symmetry breaks? What happens when balance tips just slightly out of alignment? Because the universe we know, with its stars and planets and life, exists not because symmetry held, but because it failed. Let's drift into that mystery now. Did the universe begin because symmetry was broken? Imagine a moment of perfect balance, complete stillness, no motion, no change, no time. If the universe had remained in such a state, nothing would have ever happened. No stars would ignite, no atoms would form, no consciousness would arise to wonder why. Only silence, endless and unchanging. But that's not what occurred. Instead, the universe began with an imperfection, a tiny asymmetry, a crack in the mirror of perfect order, and from that single flaw, everything unfolded. In physics, symmetry means that the laws of nature behave the same way in every direction, at every point, for every observer. When symmetry is perfect, nothing has a reason to change. But when it breaks, even slightly, motion appears, structure emerges, time gains direction. The early universe, in its first fractions of a second, was unimaginably hot and dense, a roiling plasma, where the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into one. As the universe expanded and cooled, these forces began to separate. This process is called spontaneous symmetry breaking. It shaped everything, from the structure of atoms to the formation of galaxies. The European Space Agency's Planck mission mapped the cosmic microwave background, the faint afterglow of the Big Bang, a snapshot of the universe when it was only 380,000 years old. What they found was astonishing. The temperature across the entire sky was uniform to 1 part in 100,000, nearly perfect, but not quite. Tiny variations existed, minute differences in density. These fluctuations, these broken symmetries, became the seeds of all cosmic structure. Regions slightly denser than their surroundings attracted more matter through gravity. Over millions of years, they grew into the first stars, then galaxies, then clusters of galaxies. Without those initial imperfections, the universe would have remained a smooth, featureless fog forever. But the most profound symmetry breaking happened even earlier, in the first moments after the Big Bang. According to the standard model of particle physics, matter and antimatter should have been created in equal amounts. When they meet, they annihilate, releasing pure energy. If perfect symmetry had held, every particle would have found its antiparticle. They would have destroyed each other, leaving nothing but light. Yet here we are. made of matter. This means something tipped the balance. Some unknown mechanism favored matter over antimatter by the tiniest margin. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. After all the annihilation, that single extra particle survived. And from those survivors, the entire material universe was born. Every atom in your body, every star in the sky, every planet, moon, comet, and speck of dust, all of it exists because symmetry broke in a way we still don't fully understand. Scientists call this the baryon asymmetry problem. It's one of the deepest mysteries in cosmology. Various theories attempt to explain it. Some involve exotic particles that existed only in the early universe. Others propose that the laws of physics themselves have subtle asymmetries we haven't detected yet. But the core truth remains. Without this imperfection, the universe would be empty, filled only with radiation, no structure, no chemistry, no life. Broken symmetry is the reason you can take a breath, the reason stars shine, the reason anything exists at all. Even the fundamental forces that govern reality emerged from symmetry breaking. In the extreme heat of the early universe, electromagnetism and the weak nuclear force were unified. As the cosmos cooled, they separated. This separation gave mass to certain particles through interaction with the Higgs field. The Higgs boson, discovered at CERN in 2012, is the quantum excitation of this field. It's the mechanism that broke the symmetry between massless and massive particles. Without it, electrons would have no mass, atoms couldn't form, chemistry would be impossible, the universe would consist only of particles flying at the speed of light, forever dispersing, never coalescing into anything stable. This pattern repeats across every scale. Galaxies form because density fluctuations broke the smooth distribution of matter. Stars ignite because clouds of gas collapse unevenly. Planets coalesce because tiny grains of dust stick together asymmetrically. Life itself may depend on molecular asymmetry. Amino acids, the building blocks of proteins, come in two mirror image forms, left-handed and right-handed, chemically identical. But biological systems use only left-handed amino acids. Why? We don't know. But this asymmetry is essential to the way life is structured. It suggests that even at the molecular level, broken symmetry creates the possibility for complexity, for organization, for evolution. There's a philosophical weight to this. A universe of perfect symmetry would be static, beautiful perhaps, but sterile. Change requires imbalance. Growth requires imperfection. Consciousness requires structure, and structure can only arise when uniformity fails. In a strange way, we owe our existence to a cosmic mistake, a flaw in the fabric of creation. If the Big Bang had produced a perfectly symmetric universe, there would be no one to contemplate it. No observers, no questions, no wonder. The fact that you can ask, why does anything exist, is itself evidence of asymmetry, because symmetry asks nothing, requires nothing, becomes nothing. This realization can be oddly comforting. You are not an accident in the sense of being random or meaningless. You are a consequence. The universe, through its broken symmetries, inevitably produces complexity. Stars must form, elements must fuse, planets must gather around them. Chemistry must become biology, and biology, given enough time, must become awareness. You are what happens when the universe breaks its own rules, just enough to allow structure, just enough to permit wonder, just enough to make existence interesting, rather than eternal and empty. But here's where the mystery deepens even further. If everything that exists emerged from broken symmetry in the early universe, then every motion, every spin, every rotation is also a consequence of those primordial asymmetries. The angular momentum of galaxies, the rotation of stars, the spin of electrons, all of it traces back to the first moments when uniformity cracked, when the cosmos chose motion over stillness, change over permanence, and in doing so, it set the stage for everything that would follow. So when we wonder who controls the spin, perhaps the deepest answer is this: no one controls it, because control implies intention, guidance. But the universe doesn't need guidance. It unfolds according to principles embedded in its structure from the beginning. Symmetry breaks, angular momentum conserves, space-time curves, and from those simple laws, unimaginable complexity emerges. Galaxies spiral, planets rotate, atoms vibrate, life awakens. All without a designer, all without a plan. Just the inevitable consequences of physical laws playing out across billions of years. Yet there's something miraculous in this. The universe is self-organizing. It creates order from chaos, structure from randomness, awareness from unconscious matter. And it does this not despite its imperfections, but because of them. The broken symmetries that allow matter to exist, the uneven distribution of mass that creates gravitational wells, the asymmetric molecules that enable biological chemistry. Every flaw becomes a feature. Every imperfection becomes a possibility. Every crack in symmetry becomes a doorway to something new. Take a moment to absorb this. The reason you exist is because the universe couldn't maintain perfect balance. It stumbled, tilted, broke its own symmetry, and in that breaking, it became capable of producing stars, planets, oceans, forests, minds. You are not separate from this process. You are the process, becoming aware of itself, the universe's way of noticing that it broke symmetry, and that the breaking was not a failure, but the beginning of everything beautiful. And this leads us to perhaps the most haunting question of all. If we are the universe observing its own motion, if consciousness is matter becoming aware of its rotation, then what does that make us? Are we merely passengers on a spinning rock? Or are we something deeper? Something the cosmos has been building toward since the first symmetry cracked. Let's explore that mystery together. Are we the universe remembering its own motion? Every atom inside you is spinning, not metaphorically, actually spinning. The electrons orbiting your nuclei carry angular momentum. The protons and neutrons within those nuclei rotate. The quarks deep inside them vibrate with energy that includes rotational components, all of it in ceaseless motion. And that motion isn't random. It's a continuation, an echo of the universe's first rotation. When you move, when you breathe, when your heart beats, you're not separate from the cosmos. You're part of its oldest memory, motion itself. In physics, angular momentum is the persistence of spin, the rule that keeps motion alive across cosmic time. It's conserved, meaning it cannot be created or destroyed, only transferred. Every rotation in the universe, from the grandest spiral galaxy to the smallest subatomic particle, is part of one continuous flow, a current of motion that has never stopped since the Big Bang. NASA's Goddard Space Flight Center explains it simply. Angular momentum is distributed, not lost. It flows from one system to another, from collapsing gas clouds to forming stars, from exploding supernovae to newborn solar systems, from stellar cores to planetary orbits, from molecules to living cells. The spin never truly ends. It only changes form. Measurements from the European Space Agency's Planck satellite reveal something extraordinary. The cosmic microwave background, that faint afterglow from the universe's infancy, contains subtle directional patterns, anisotropies, slight differences in temperature that hint at rotational motion in the early universe. Some cosmologists interpret these as traces of primordial, angular momentum, the original twist that set everything in motion. That ancient spin never vanished. It fragmented, spreading across scales, from galaxy clusters to individual atoms, each carrying a fragment of that first rotation. When stars form, vast clouds of hydrogen and helium collapse under their own gravity. As they shrink, they spin faster. Angular momentum must be conserved, like an ice skater pulling her arms close to her body. This same principle gives rise to accretion disks around young stars, swirling vortices of gas and dust. From these disks, planets are born, each inheriting a portion of the original spin. Our solar system formed this way 4.6 billion years ago. Earth's rotation, the Moon's orbit, the tilt of Saturn's rings, all echoes of that primordial whirlpool. And within those planets, inside every rock and ocean and living cell, the pattern continues. At smaller and smaller scales, the atoms in your body hold rotational memory. Electrons that define chemical bonds obey a quantum property called spin. It's not literal spinning in the classical sense, but it is a fundamental angular momentum, an intrinsic property that determines how particles interact with magnetic fields, how they bond, how they create the structures necessary for chemistry, for life. Without spin, atoms couldn't form stable configurations, molecules couldn't bind, DNA couldn't twist into its elegant double helix. NASA's quantum research initiatives describe spin as the engine of atomic structure, the difference between chaos and stability, between formless plasma and organized matter. In this sense, every piece of matter carries an ancient choreography. The spin of particles leads to magnetic fields. Magnetic fields lead to molecular structures. Structures lead to stars and planets, and eventually to life. Your neurons fire using electrical potentials shaped by these electromagnetic forces. Every thought that crosses your mind is built on alignments of charged particles, cascades of ions flowing across cell membranes, creating patterns, rhythms, a kind of ordered motion that emerges from quantum spin. So when we ask whether consciousness might be the universe remembering its motion, the question isn't purely poetic, it's physical. Each brainwave, each neural signal, built upon rotations that have existed since the dawn of existence. The magnetic fields generated by your thoughts are faint echoes of the same electromagnetic principles that guide pulsars, that shape the auroras on Jupiter, that carve spiral patterns into distant galaxies. The astrophysicist Neil deGrasse Tyson said it beautifully. We are not in the universe, we are part of the universe, and the universe is in us. From a scientific perspective, memory is pattern preservation, information encoded in physical states. Atoms remember through spin orientation. Magnetic domains in rocks remember Earth's ancient magnetic field. Stars remember through rotation curves inscribed in their motion. The universe remembers through the geometry of space-time itself. Einstein's general relativity teaches that energy and momentum shape space-time's curvature. Every movement leaves an impression, a subtle distortion in the fabric of reality. Rotation creates something called frame dragging, the twisting of space-time around massive spinning objects. NASA's gravity probe B confirmed this in 2011. The experiment measured how Earth's rotation warps the space around it. Like a spoon stirring honey, it proved that spin isn't confined to objects alone. It extends into the very structure of the cosmos. Your movements, though infinitesimal compared to planetary rotation, also disturb space-time. The difference is only scale. Your body's atoms spin billions of times per second, generating magnetic interactions measurable by quantum sensors. Each micro-rotation contributes to the ongoing record of motion, a record that extends back before humanity existed, before Earth formed, before the sun ignited. If all motion leaves traces in space-time, then perhaps what we call awareness is simply the universe perceiving those traces through us, not as emotion, not as spirit, but as physical continuity, matter recognizing its own persistence. Consciousness, in this purely material sense, is a system's capacity to reflect its internal state, and that reflection is written in movement, neural oscillations, electrical pulses, chemical gradients shifting and flowing, all forms of motion, all descendants of the universe's primordial spin. Even light, the messenger of the cosmos, carries angular momentum. Photons possess spin, a quantum property that determines how they polarize and interact with matter. Polarization patterns across the cosmic microwave background act as the oldest record of rotational memory in existence. The Planck satellite and NASA's WMAP mission mapped these swirls in exquisite detail, showing faint spiral patterns, signatures of gravitational waves rippling from the universe's first moments. When you gaze at starlight, you're literally seeing the memory of spin, light twisted and stretched by billions of years of motion. That light enters your eyes, triggers chemical reactions in your retina, becomes electrical signals in your optic nerve, and eventually becomes part of your conscious experience. In that way, the universe doesn't just remember its spin, it continues to experience it, through every observer it creates, through every conscious being that arises from its matter and energy. You are not merely observing the cosmos, you are the cosmos observing itself, recognizing its own rotation, feeling the ancient rhythms still pulsing through space-time. Even as the universe expands and cools, these patterns persist. Galaxies may slow over billions of years, but their angular momentum never disappears. It transfers to intergalactic gas, to dark matter halos, to the radiation that fills the voids between stars. The James Webb Space Telescope has detected faint filaments of gas stretching between ancient galaxies, structures shaped by those transfers of spin. Every wisp of matter still moves to the rhythm established 13.8 billion years ago. And when the last stars fade, when the universe grows cold and dark, those patterns, encoded in gravitational waves, particle spin and frozen light, will still ripple faintly through empty space. They won't be gone. They'll be written into the shape of everything that remains. Like fossils of rotation, the universe's deepest form of memory, motion preserved as geometry. Carl Sagan once reflected on this. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. In the language of physics, that knowing isn't mystical. It happens through motion, energy, and spin. The universe continuously encodes and retrieves its own history through the formation of structure, through the evolution of complexity, through the emergence of minds capable of contemplating their own origins. Take a slow breath. Feel the air filling your lungs. Every atom in that oxygen molecule once belonged to a star, It fused in a stellar core that was itself spinning. That core's angular momentum flowed into the supernova that dispersed those atoms across space, flowed into the molecular cloud that collapsed to form our solar system, flowed into the Earth, into the oceans, into the first living cells, into the evolutionary chain that led to you. You are a moving archive, a living fragment of the universe's ongoing memory. The same rotation that ignited the first stars still turns within you, in the spin of your electrons, in the firing of your neurons, in the beating of your heart. You are not separate from cosmic motion. You are a continuation of it, an expression of it, a moment when the universe pauses just long enough to recognize that it's still spinning and always has been. And perhaps that recognition, that brief flicker of awareness in the vast darkness, is the most profound thing the universe has ever accomplished. Not because it's supernatural, but because it's inevitable. Given enough time, matter organizes itself. Atoms become molecules. Molecules become cells. Cells become organisms. Organisms become minds. And minds become windows through which the cosmos sees itself. So when you close your eyes tonight and feel the stillness settling around you, remember this: the stillness is an illusion. You are spinning. You've always been spinning. The quiet you hear is the whisper of everything turning in perfect harmony, from the quantum foam beneath reality to the spiral arms of distant galaxies, all of it connected, all of it moving, all of it remembering. And you, right here, right now, are part of that memory. You are the universe's way of understanding its own motion. Every breath you take participates in a rhythm older than time itself. Every thought you think emerges from rotations that began before atoms existed. You belong here. You are part of the eternal dance. Your existence is both consequence and continuation of the same cosmic motion that started at the very beginning. The spinning never stops. The dance never ends. And within that endless turning, you have found your place, your rhythm, your home in the vast symphony of everything that moves. Rest in that knowledge. You are exactly where and when you're meant to be, spinning gently through space and time, part of something infinitely larger than yourself, yet intimately connected to every rotation in the universe. The cosmos turns. You turn with it, and in that shared motion, despite all the chaos and uncertainty, despite every question that remains unanswered, all is well. All has always been well, because motion continues, memory persists, and the universe, through you, remembers how it began, with a single perfect spin that has never stopped turning. If this quiet journey has brought you even a small moment of peace, I'm deeply grateful you've spent it here with me. A gentle subscription would mean more than I can express. It keeps these meditative explorations alive. Each notification becomes a reminder that somewhere in this spinning cosmos, gentle souls still seek wonder in the deep questions. And if you're kind enough, leave a comment telling me where you are and what time it is as you listen. I love knowing how far these stories drift across our rotating world, from one quiet corner to another. Your presence, your words, even your silence, they guide me forward like distant stars. Until we meet again, may the universe turn softly around you. May you rest in the knowledge that you're part of something ancient and endless. And may you sleep well, knowing that every atom within you remembers the cosmos, and the cosmos, through you, remembers itself. Good night. Sweet dreams.